Hello and welcome to this video for the 2022 Scholarship Physics paper. So for this paper, I'm just going to split it into two separate videos. So for video 1, the one you're watching right now, I'm just going to go through question 1 and question 2. And for the second part of the video, I'll be going through question 3 and question 4. And that's only because this paper is a bit longer than standard NCEA papers. And I don't want the video to drag on for like more than an hour. And I prefer to just have two shorter videos. So maybe it's easier to concentrate on the questions without having to sit through one like 2-hour video. Maybe two shorter videos is a bit more easy to focus on the content. And without further ado, let's just get into it. So let's look at question 1, photons, and below that we have some data that we might need for this question. So question A, the description of the photoelectric effect and the Bohr model of the atom both involve the concept of quantization of energy. There are similarities and differences in how this context is applied in these contexts. Describe one difference in the use of concept of the quantization of energy between the photoelectric effect and the Bohr model of the atom. So for the photoelectric effect, we have some material here. Material, probably usually it's a metal, so we have some say metal here, and we have some light that's going to be incident on the metal, and there's going to be some certain amount of electrons that are within the metal, and some of these electrons, they can absorb the energy of the photons, and this energy, if it is greater than the work function or the minimum amount of energy to remove it from the material, then they can actually be removed from the material and have a certain kinetic energy as it leaves the material, and this is only given that if the energy of the light is greater than that of the work function of the metal. If not, then the light will be unable to remove these electrons from the material. So that's in terms of the photoelectric effects. It's a very brief explanation. In terms of the Bohr model of the atom, it states that there is multiple discrete energy levels. Multiple discrete energy levels that are around the nucleus. So we have, in this case, we might have an electron at this energy level. And he states that this electron can absorb some energy from a photon. And if that energy, so if some energy is exactly equal to the difference in the energy between two levels, then that electron can be excited to a higher energy level. So this electron can absorb a photon and absorb that energy to move to a higher energy state. Or conversely, it can release a photon of some energy and then excite back down to a lower energy state. So if the energy is equal to some n1 minus n2, exactly equal to that discrete amount of energy between the levels, then there's possibility that the electron can be excited by that photon to a higher energy level. So in terms of the differences, I would say there are quite a few, but in terms of just mentioning one difference, then it shouldn't be too difficult. So in terms of the main difference, this photoelectric effect is mostly about just moving electrons from a material or metal, but for the Bohr model, we're talking about an atom and how electrons can be excited to a higher energy state if the energy of the photon is exactly equal to the difference between those energy states. So for the terms of the answer, we can say P. So PE is in the shortened form of photoelectric effect. So it is quantization of energy of light being absorbed by electron, to be removed from a material or metal. For the Bohr model of the atom, we're talking about the quantization of the energy of an electron. So in terms of, for Bohr's model, refers to energy from one energy level to another. And in terms of the energy, we can talk a little bit about how for the photoelectric effect, as long as the energy of the photon is greater than that of the work function, then the electron will be removed from the metal. But for the Bose model, the energy of the photon must be exactly equal to that difference between the discrete energy levels. So I don't really have enough space to write that, but that could be another difference you can talk about in terms of the quantization of energy and the differences between the photoelectric effect and the Bohr model of the atom. But in terms of this is a very just basic explanation, and you don't need to go too much in detail since you have 3 hours in the exam, so maybe it's not super a lot of time given the amount of stuff you have to do. So in terms of these types of questions, just 1 mark questions, just keep it short. So this is just a 1 mark question. And the answer they have on the schedule is even more brief than what I've got there. So it just talks about PE. So photoelectric effect is the quantization of energy of light, photons, but the Bohr model is the quantization of energy and electrons. It's even more brief than what we have here. And this is just a very not straightforward, but very standard 1 mark question. Very, very common for them to be asking about the photoelectric effect and the Bohr model of the atom. So these are two pretty common questions that we'll ask. So it's good to, when you're revising, to revise on these concepts for the exam. Good question B. So a laser typically consists of a medium that emits light between 2 mirrors that form a cavity, as illustrated on the right. The cavity is similar to a closed box for the emitted light waves. The light emitting medium can emit a continuous spectrum of light within a narrow range of wavelengths. The minimum is 480 nanometers and the maximum is 490 nanometers. And the cavity is 5 centimeters long. Some wavelengths within this range are able to form standing waves within the cavity. These are called standing wave modes. So calculate the total number of standing wave modes possible in the cavity within the emitted 480 to 490 nanometer range. So the first thing to note here is that the mirrors are probably going to be acting as fixed edges. So when the light reflects on the fixed edge, it's going to undergo a 180 degree phase change. So 180 degree phase change upon reflection. So therefore, incoming waves is going to be interfering destructively with the reflected waves, and therefore it will be creating nodes at the 2 endpoints of the mirrors. So this will be a node and a node here, and node here. And in terms of the So in terms of what we can do here, so I would just suggest you draw quick diagrams of the first couple of harmonics of this situation. So if you have the first harmonic, it's simply just going to be node at both ends, and this will be here. Sorry, apologize for the poor drawing, but hopefully you can see what I'm trying to get at. Maybe a bit bigger would be good. So for the second drawing, we'll look at the second harmonic. So this will be a node in the middle with 2 nodes at the 2 fixed ends. So we're going to have... Sorry. Yeah, my drawings are not the best, but hopefully still relatively clear. So, okay. For the third one, we'll have, again, 2 nodes at the 2 fixed ends. And it's going to be 1 and 2 nodes in between. Maybe something like my drawing is not very good. Okay, sorry, apologies, just forgive me for it's not very good drawing, but hopefully you can see what I'm trying to do. Okay, yeah, so these should be equal sized gaps here, but obviously my drawing here isn't the best, but hopefully you still get what I'm trying to say. So in this case, we know L is equal to lambda over 2. So in this case, lambda equals 2L. For this case, we see that this is exactly 1 wavelength within the whole length of the pipe. So this is just L equals to lambda, and this is therefore lambda equals to L. For the third case, we have exactly 1.5 wavelengths within the full length. So therefore, we see that L is equal to 3 over 2 lambda. So 3.5 wavelengths fit into the the whole length of the medium. And in this case, we have lambda equals to 2 over 3 L. And hopefully we can see a little bit of a pattern here. So we have lambda equals 2L, lambda equals to L, and lambda equals to 2 over 3L. So in this case, we can rewrite L as 2L over 2. This is 2L over 1 and 2 over 3L. So as you can see, the general pattern here is just going to be n times some lambda, where n is some integer, and that's going to be equal to 2 times of the length of the medium. So that's going to be the general pattern that we're going to be observing in this situation. And to find the number of modes in between, we're simply just going to substitute the upper bound wavelength, which is 490 nanometers, and we're going to substitute the lower bound, which is 480 nanometers, into the equation. We're going to find the difference between the number, those two numbers, and that's going to be how many modes are in between, and that will be representative of the total number of standing wave modes that are possible within the two possible wavelength ranges. Okay, so we run out a little bit of space. I'm just going to remove some of this. Okay, so in this case, if we have 480 nanometers, we're going to have n lambda equals to L. So therefore, L is 5 centimeters, which is 0.05 meters. So we have 2 times 0.05 divided by the wavelength, which is 480 times 10 to the power of -9. And that is going to be N1. So N2 is 490 nanometers, and N lambda equals to 2L. So 2 times 0.05 divided by 490 times 10 to the power of -9. So that's N2. And this N1 is equal to, if you put into a calculator, it's going to be equal to 208,333. So 208,333. And for 490, it's going to be equal to 204,082. And all we need to do now is just need to find the difference between them. So difference is equal to the bigger one minus the smaller one. So 208,333 minus 204,082. And therefore, this will be equal to 4,251 modes allowed. Yeah, so this will be the number of modes that are allowed. And this is a 2-mark question. So if you get the correct answer, you will be getting two ticks here. Let's have a look at question C. Okay, the process of nuclear fusion in the sun releases energy which spreads through space in the form of electromagnetic radiation. The photons that make this radiation carry momentum as well as energy, with the momentum per photon is given by P equals to Planck's constant over the wavelength. And the sun loses 4.3 times 10 to the 9 kilograms of mass per second due to nuclear reactions. Estimate the force exerted on the Earth by the photons as it receives from the sun. Okay, so we're going to have the sun. So we're going to have sun. Not a great drawing, but again, just stay with me. So sun. And we're going to have some much smaller Earth here. And it's going to be some photons released on the Earth. And there's going to be these photons are going to be carrying some momentum when it reaches the Earth. And once it reaches the Earth is going to absorb that amount of photons. And we'll assume that once the photons are absorbed, it's going to lose some momentum that's going to be equal to its initial momentum. So basically, at the end, it's not going to have any more momentum after it's being absorbed by the Earth. And as we know, if there is a change in momentum, then over some period of time, then there's going to be a force exerted on the Earth. So and that obviously will depend on how many of these photons are being absorbed per second. And using we can use this per second concept to calculate the average amount of force that the Earth was going to be it's going to be the average force the photon is going to be exerting on the Earth. Okay, so in terms of calculating the number of photons that are going to reach the Earth, it's about calculating the total amount of photons. So we're going to be like question mark, how many photons are released by the sun? So that's something we need to find out. We also need to find out what proportion of these photons are actually reaching the Earth. It's because the sun is very, very big and the Earth is much smaller and it's quite far away. So not all of those photons are actually going to reach the Earth. So there's going to be a large majority of those photons are not even going to reach the Earth. So we're going to have to ask us what proportion of photons actually reach the Earth. So what proportion of photons actually reach Earth? And then after we have that, we can calculate the total number of photons. So now we can say, now we know the total number of photons, and then using the momentum of each photon, we can calculate the average impulse of the photons on the Earth. Okay. So those are the questions we probably want to answer. So we can start off with trying to calculate how many photons are actually released by the sun. And we can do that because the question tells us how many kilograms of mass is lost per second. So we know sun loses 4.3 times 10 to the power of 9 kgs per second. And we know that E is equal to mc squared. And we also know that E equals to some h times f, so Planck's constant times the frequency of the photons. So in this case, we can actually find how much of the energy is being converted from mass into energy. So in this case, it's E equals to the total mass, which is 4.3 times 10 to the 9, multiplied by C, which is 3 times 10 to the power of 8. I believe that's what they're using here. Yeah, 3 times 10 to the 8. 3 times 10 to the 8 squared. And this is going to be equal to 3.87 times 10 to the power of 26 joules per second. And we can convert this to how many photons are released by the sun per second, because we know that the energy of a single photon is going to be equal to Planck's constant multiplied by the frequency of that photon. Okay, so in this case, we say that 3.87 times 10 to the 8, not 10 to the 8, 10 to the 26 is equal to 6.67. What was that? 6.67 times 10 to the negative 34. So times 10 to the power of negative 34 multiplied by the frequency of light. But in this case, we can know that V equals to F lambda. So in this case, we can rearrange to find the frequency, which is just going to be V over lambda. So in this case, it's 3 times 10 to the 8 divided by wavelength, which in this case is 550 nanometers. Okay, so 550 times 10 to the power of negative 9. Okay, and that will give us the number of photons being released per second. So in this case, it will be times. Okay, so this is the so what we have here right now is the energy per photon, and there's going to be some n number of photons that are going to be released per second, and we're just going to be rearranging to find n. So n in this case will be equal to 1.07 times 10 to the 45 photons per second. Okay, so that's the total number of photons being released by the sun each second. And as we said before, the second question we need to answer is what proportion of the total emitted photons from the sun are actually reaching the Earth? And I'm just going to hopefully just remove this top working here. We just remember the answer, which is 1.07 times 10 to the 45. So that's how many photons are being released per second. Okay, sorry, just bear with me. Okay, so in terms of the number of photons, we know that the sun is going to have some surface area, so some surface area which is equal to 4 pi r squared, so some SA which is going to be equal to 4 pi r squared, and it's going to be some distance away. There's going to be some small Earth here, and of the total number of area that this covers, that the Earth is going to inhabit some of that area, that the total amount of photons will be dispersed in this amount of area and that radius. So we have 1.5 times 10 to the power of 11, which is the distance, a mean distance from the Earth to the sun. So it's going to be a whole range of apologies for my poor drawing. So it'll be a whole range where all possible photons of the sun can be, and the Earth is going to be representative of some small area of that which does reach the Earth. So we know that the SA is 4 pi r squared, and we know the area is just pi r squared. So in this case, the Earth is going to have some proportion of the total surface area, which is going to be pi r squared over the 4 pi r squared, which is the total surface area of this bigger circle we see on the outside. So in this case, SA is going to be equal to 4 pi times of the radius, which is equal to the distance between the Sun and the Earth, which is 1.5 times 10 to the 11 squared. And the area will just be equal to pi times 6.37 times 10 to the power of 6 squared, and 6.37 times 10 to the power of 6, that is equal to the radius of the Earth. And this area is going to be some proportion of the overall area that the photons can be. So therefore, the proportion is going to be equal to some pi times squared divided by 4 pi multiplied by 1.5 times 10 to the power of 11 squared. And this will be equal to 4.51 times 10 to the power of negative 10. So therefore, that is the proportion of photons actually reaching Earth out of the orbit. So that's the total proportion. And so therefore, the total number of photons actually reaching Earth would be the total number multiplied by that proportion. So the overall n reaching Earth, so n Earth, is equal to 1.07 times 10 to the 45 multiplied by 4.51 times 10 to the power of negative 10. And that is going to be equal to 4.82 times 10 to the power of 35 photons per second. And now, to be honest, I think, in my opinion, that's actually the hard part done. The rest is actually very simple, in my opinion. So now all we need to do is just calculate the momentum of each photon and then calculate the change in momentum per second, and which will be the impulse or the force on the Earth. So in this case, we have 4.82 times 10 to the power of 35 photons per second. In terms of the momentum, that's equal to 6.63 times 10 to the power of negative 34 divided by the wavelength, which is 550 times 10 to the power of negative 9. And that is going to be equal to 1.21 times 10 to the power of negative 27 kilograms meters per second. And that will be the momentum of a single photon. So you need to multiply by the total momentum imparted to the Earth in 1 second, which is going to be 1.21 times 10 to the power of negative 27 times the number of photons that are actually reaching the Earth per second or being absorbed by the Earth per second, which we just calculated is 4.82 times 10 to the 35. And that is going to be equal to 5.84 times of 10 to the 8. So that will be the change in momentum. So this is equal to the change in momentum per second. So in this case, this will be change in P. And this will be per second. And we know that the force exerted on the Earth, which is the rate of change of momentum. So force is just the rate change of momentum. So in this case, over 1 second, we know this is the amount of momentum imparted in 1 second. So therefore, the force will just be equal to 5.84 times 10 to the 8 newtons. Okay, so sorry, the working got a little bit messy, but hopefully that makes sense there. So the force is 5.84 times 10 to the power of 8 newtons. And this is a 3-mark question, I believe. Yeah, this is a 3-mark question. So you can get up to 3 marks for this question. And I'm pretty sure if you can get up to 2 marks, 2 marks is actually attainable even if you don't calculate the proportion correctly. So if you calculate the proportion incorrectly, I believe you can still get 2 out of the 3 marks. So in terms of scholarship, even if you don't understand the whole question, if you understand only a small part of it, still try to put that down because, for example, this 3-mark question, even though I would say calculating proportion was the hardest part of the question by far, even if you couldn't do that, you could still score like a 67% on the quiz, like 2 out of the 3 marks. So just keep that one in mind. So just anything you think you know, just jot it down. Don't leave anything blank. Because generally, if you start leaving things blank, it becomes really difficult to attain any of the high scores that you really want to. Okay, look at DI. So comment on the significance of the size of the force exerted on the Earth by the photons. So just by not looking at this question, I assume it's going to be some very small negligible amount of force, because if not, I think the Earth will be flying around all over the place, which is not good. So I assume, so just by not looking at the question, our common sense will tell you that this force is probably going to be negligible. And it's always good to try to think in terms of common sense, is because if you get an answer for a question that contradicts your common sense, it's usually a red flag to maybe go check your answer. So if I somehow got a force that's super massive, and somehow like it'll mean that the Earth is flying away at like 3,000 meters per second, I'll definitely know that that's probably not the case, and you probably did something wrong. So usually, my experience with this scholarship is usually trusting your instincts usually does work, and once you get your answer, it's always good to do a reality check with yourself. So that's just my guess. Having not really done any calculations, my guess is the force is probably not going to be very significant. So in terms of significance, probably the best thing we can probably look at the acceleration on the Earth. So let's see how fast it's accelerating. So in this case, it's F equals to ma. So in this case is A equals to F over m. And the force imparted is 5.84. That's very messy. Sorry, that's very... Okay, I did it again. Okay, my bad. Okay, 5.84 times 10 to the power of 8 divided by the mass, which was... What was the mass of the Earth? The mass of the Earth is 5.98 times 10 to the 24. And that is going to be equal to 1 times 10 to the power of negative 6 meters per second squared. So as you see, that's insanely small. That's 0.00, like 15 zeros, and then a 1. So that's very small. That's basically negligible. So my initial prediction is valid. Well, not valid, but my initial prediction was correct. So that's just very insignificant. So very insignificant acceleration. Okay. So question II. If the Earth was covered by ice, it would be more reflective. Explain how this would affect your answer to part C. Okay, so in terms of if the Earth was being more reflective, this means that some photons will not be absorbed by the Earth, and some will actually be reflected away. So there's going to be a change of impulse, higher change of momentum, since there's going to be some momentum going into the Earth, and then after it's reflected, it's going to go back traveling in the opposite direction. So the change in momentum is actually greater, and therefore if the change in momentum is actually greater, then we expect there's going to be a higher force. So we have like an Earth here. So initially what we were assuming, so initial assumption was just going to be some photons arriving on the Earth. It's going to have some momentum we're going to call P. And once it arrives on the Earth and is absorbed, we assume that P is 0. So all of that momentum is gone after it's been absorbed by the Earth. So therefore the overall change in this case, the overall change of momentum was just equal to the initial momentum, since the final momentum is 0. However, if the momentum, if the photon is reflected, so it's going to be some photons going back, there's going to be some P, we're going to call it P, PF, that's going to be greater than 0, that's going to be greater, and the change in momentum is therefore going to be greater. So the change in momentum will actually be, in terms of the magnitude of the change in momentum, so magnitude will actually be the initial momentum plus the final momentum, assuming that they're going back exactly the same direction, then we assume that the magnitude is actually the sum of these, which is actually greater than the initial momentum, as sum final is greater than 0. So hopefully I've illustrated why this is the case. So the overall change in momentum is greater, and with a greater change in momentum, we would expect a larger impulse, and therefore the force on the Earth would increase. So would expect photons. We would expect photons to have greater change in momentum. Greater change in momentum as it's reflected. As it is reflected. As it is reflected. So therefore, more momentum is transferred. So more transferred. So therefore, the force on the Earth would increase. Yeah, and that's really the answer to this question. Okay. In terms of the marking for this question, I believe it's 1 mark each. Okay, so 1 mark for say insignificant acceleration will give you a mark, and saying that there's going to be an increased force imparted on the Earth with a greater, with a valid explanation, that's going to get you 1 mark as well. And obviously, this whole question is out of 8 marks. And I believe that's correct. Yeah, 8 marks in total. Alright, so let's have a look at question 2 for the waka. Sorry, if I pronounce anything incorrectly, feel free to correct me in the comments. I'm not very good with pronunciation, so apologies in advance if I pronounce anything incorrectly. Again, feel free to point it out in the comments below. So in terms of, I'll try my best. Okay, so question 2, we're going to look at the waka horoa. Sorry, again, I apologize. I'm really not good at pronunciation. So the history of sailing in New Zealand goes right back to the original settlement by ancestors of Maori more than 700 years ago. The ancestors from Polynesia designed double-hulled boats with a triangular sail. I'm just going to say WH because I don't want to continuously pronounce something incorrectly. So I'm just going to say it's for WH, that were strong, stable, and most importantly, able to sail through the wind. This allowed them to carry out exploratory voyages. From such exploration, they were able to plan and carry out their migration to Aotearoa. WH are able to sail against the wind by heading at an angle to the wind, as shown in the simplified diagram below to the right. As measured by a stationary observer, the initial wind velocity is 10 meters per second from north. The velocity of the WH is 6 meters per second to the northeast, and the final wind velocity is 10 meters per second towards the southwest. And it's in the opposite direction to the velocity of the WH. By considering the wind direction before and after striking the sails, use impulse and momentum to explain how the wind produces a force on the sail. Okay, so in this case, if you look at just the magnitude of the change in the speed, it's actually just no change in the magnitude of the speed. The initial wind velocity is 10 meters per second, and the final wind velocity is 10 meters per second. However, we need to remember that momentum is a vector quantity, so it has both size and direction. And in this case, the direction of the wind has indeed changed. So therefore, the momentum of the wind has therefore changed as well. And as we know that if there is a change in momentum, there will be some force that's going to be imparted onto the sail. So basically, we're just going to be saying that, mentioning that momentum is a vector quantity, has both direction and magnitude. Magnitude doesn't change, but the direction did. So there is a change in momentum. So therefore, there's going to be some reaction force on the sail. Okay. So, say. Momentum is a vector quantity. So there is both plus direction. So there's both size and direction. So there's a change in direction, hence there's a change in momentum. Change direction directly implies a change in momentum. Change implies a change in momentum. So therefore, there's going to be some force onto the scale, the sail. So there's going to be therefore a reaction force. And that's all we need to say for this question. So vector quantity, just change in momentum, and hence there's a reaction force onto the sail. And I believe this is a 1 mark question. Yep, this is a 1 mark question. So there's a change in momentum, so therefore there's going to be some reaction force there. Okay. So question II, explain how the wind produces a force on the WH that has a component in the direction that it is traveling. Use the grid below to draw a vector diagram to help your explanation. The vectors for the initial wind velocity, v of wi, and the final wind velocity, v of wf, and the velocity v of the wh are drawn onto the grid to help you. Start your answer by finding the vector for the change in the velocity of the wind. Okay, so for this question, there's going to be, so what we're trying to find is just there's going to be some component of the reaction force that's going to be in the same direction that it is traveling, and hence it's going to just going to be increased speed in that direction due to that force. All right, so in terms of the change, what we want to do is we're trying to find the change in the velocity of the wind, and therefore there's going to be an opposite reaction force exerted by the sail, and some component of that force will be in the same direction that the WH is traveling in. So we know that the change in velocity is equal to the final minus the initial as a vector. So in this case, if we have a Vf minus Vi, that's equal to Vf plus Vi in the opposite direction. So this, if we had Vi in this direction, then if we add, then we need to reverse the direction. Okay. So this is equivalent to Vf plus Vi, but where Vi is opposite direction. So we can just do a vector addition here. So we have Vf and the reverse of Vwi will just be this vector here. So in this case, we can do an addition. I can do the addition. This will be negative Vwi, so Vf plus Vi. And then we can find the change in velocity, which will be this vector here will be the change in V. This will be some change in V of the wind. So this change in V caused the wind to change its direction from Vwi to Vwf. And because of this change in velocity, there's going to be some opposite directional change in the velocity of the WH in the opposite direction, since we're assuming that there are no external forces, so therefore the conservation of momentum, there's no change in momentum, therefore there has to be some equal change in momentum of the WH in the opposite direction, so that they will cancel each other out. So overall there's no change in momentum because we're assuming there are no external forces, so conservation of momentum holds. So assume conservation of momentum. So in this case, conservation of momentum, so no external forces. And therefore there's an equal change in momentum, not necessarily equal change in speed, because the WH and the sail and the wind have different masses. So not necessarily an equal change in speed, but there should be an equal change in momentum. So equal change in momentum in opposite directions. Equal change opposite directions of the momentums. And therefore, there is some vector of speed, change in speed in the opposite direction to that of the wind. And therefore, that would be representative of the change of speed of the WH. So this would be change in V of the boat, or the WF. And as we can see here, if we look at this vector here, there's going to be some component in this direction. So some component here, and some components that's going to be there. And this component here, which I'm going to highlight in red, so this component here will be the component of force that is in the same direction of the boat. So this will be the forward component of impulse, or the forward component of the force that's in the same direction as the boat is traveling. So in terms of our explanation, we can start. Use a grid below. The vectors of the initial blah blah blah. Start your answer by finding. Okay, so we can just say I don't think we need to say too much here, since we've basically shown it in the drawing. So there is some change in V in opposite direction of the wind of the boat. So some change in V in opposite direction of wind. And this is for the So there's some change in V in the opposite direction, and therefore there is some component of that reaction So some component of that reaction force will be in the same direction that the waka hua is traveling in. So some component of the reaction force is in. Okay, and that's it for this question. Okay, so there's some change in momentum, and yeah, basically all we've said here. So assuming conservation momentum, so we'll get us our answer there. Okay, and this is a 2-mark question. So if you get everything correctly, you will get 2 marks there. Okay, so question B, the motion of the WH is combined with the motion of the wind changes, both the apparent speed and the direction of the wind hitting the sails. On board the WH, the wind appears to have a higher speed and to come from a direction further towards the front of the WH. The captain measures the wind velocity as 14.9 meters per second. That hits the sail at an angle of 28.4 degrees, as shown in the diagrams on the right. The sails have a combined area of 40 meters squared. The density of air is 1.23 kilograms per meters cubed. So in terms of the density, so the density is 1.23 kg per meters cubed. And we know that the mass is equal to the density times the volume. And the volume in this case, the volume is equal to, it's going to be equal to some area of the sails. And some area of the sails, and the area of the sails, and just going to be some like length of the wind that's going to be hitting the sails, so times some component that we're just going to say it's going to be the velocity of the air normal to the sails. So that would be how much meters of wind per second there. So it would be area of the sails multiplied by the velocity of air. Okay, so in this case, we need to be worried about the component that is normal. So this component here, my drawing is horrible. Okay, sorry. Let me try that again. Okay, so we have some component that's normal to some component that is normal to the sails, that's going to be hitting the sails, and that's the component of air that we're going to be concerned about. So in this case, we know that this angle is 28.4 degrees. So in this case, we can draw the diagrams here. Vector diagram. So this angle here would be 90 minus 28.4. That would be 72, 52, 51.6 degrees. No, 61.6 degrees there. So this component there would be okay. This probably was not the best thing to do here. Okay. Sorry about that. Okay, so what we have here will be this component here. We know that there is some component of air hitting the sails at an angle, which is 28.4 degrees from the sail, and we're trying to find the normal component here. So we know that this angle is also 28.4 degrees, alternate angles on parallel lines. And we know that this here is 90, draw 90 degrees. As we know that's 90 degrees because this component is normal to the sail. So therefore we know that sine of 28.4 is equal to O over H. So sine of 28.4 times of H, which is something, 14.9, equals to V normal. So therefore V normal It's going to be equal to 14.9 times sine of 28.4. And if I do a calculation of that, so 28 sine of 28.4. That is equal to 7.087. 0.087. So now we know that mass will be equal to density, which is 1.23, multiplied by the area, which is 40, multiplied by that V norm component. Sorry. And that is equal to, what is that equal to? That is equal to 349 kilograms. Yeah, and that's our answer for this question. So it will be 349 kilograms. And that's a 1 mark question there. So 1 mark for this correct answer. Okay. Alright, so the sideways force from the wind on the cells causes the WH to tilt over sideways. In strong winds, the upwind side of the hull may be lifted out of the water altogether. Explain how the double hull design of the WH helps stay upright in strong winds. So the double hull design just means that there's like 2 hulls on both sides. We have one here and one here. So when the boat is tilted over, we notice that on the right hand, the side is tilting over, the hull is submerged in the water. So we have some Fg. It's going to be acting, force of gravity acting on that part of the hull. And there's going to be some buoyancy force from the water. So some B from the water that's going to try to counteract that force. Otherwise, if there's no buoyancy force, then the Waka Huroa is just going to sink into the water. But obviously that doesn't happen because of that buoyancy force provided by the water. However, on the left-hand side here, this hull is not submerged in the water. So what we have here is just Fg. And there's no component of buoyancy force that's going to be acting against that Fg. In terms, now we need to look at the torques acting on the system. So this force here, okay, so center of mass perhaps is somewhere, maybe we say center of mass is somewhere here. So this will be some perpendicular distance away from the center of mass. And since there's a force acting from the center of mass, it's going to produce a torque. And in this case, we can see that there's going to be a clockwise torque produced by the force of the wind hitting the sail. So there's a clockwise torque, and that's what's causing the WH to tilt over in the first place. However, we notice that on this left-hand side here, there's going to be some force of gravity that's going to be acting. And this is going to be producing a counterclockwise torque, which is going to counteract the torque produced by the force of the wind hitting the sail. And due to that, it's going to be less likely that the hull is going to lift over the water. Since if we didn't have this hull on the side, let's say we didn't have a hull, therefore this force of gravity would be much smaller, and therefore it will be much easier for the boat to just tilt over. However, due to having that hull, there's some force of gravity, substantial force of gravity that's producing a counterclockwise torque, which opposes the clockwise torque that is tilting the boat over. So in this case, we say that force from sail, and we're just going to abbreviate that to FFS because it's not a lot of space for me to write. So force from sail is producing force some perpendicular distance away from center of rotation, center of rotation. So there's going to be a torque produced, so clockwise torque produced here. So clockwise. When it's going to abbreviate again, so that's WH for the boat because again I just don't have a lot of space to write. So when WH is tilted over, there is no buoyancy force on left side of WH. Hence, that gravitational force is going to produce a counterclockwise torque. So, hence the Fg produces a counterclockwise force, torque, which counteracts that of the force hitting the sail. So, well, I probably should say that counteracts the clockwise torque might just be better. Counteracts the clockwise. Yeah, and then you can probably mention that because there's some cancellations there's going to be less likely for the boat to tip over. Okay, and that's 1 marks for this question here. So 1 marks. If we want to explain how the tilting of the WH will affect the force produced by the wind hitting the sails. So once the boat is being tilted, there's going to be some cross-sectional area of that sail that is going to be perpendicular to that of the wind. So as we were looking before in the previous question, we were talking about the velocity of the wind that's normal to that of the sails. So if we tilt the boat, then we're going to be tilting that of the sail, and therefore there's going to be a smaller, like let's say some smaller cross-sectional area that's going to be perpendicular to that of the wind, and therefore it's going to be some less component of there'll be less mass of wind hitting, so therefore there's going to be a reduced force on the boat. Okay, so in this case, when the boat is tilted, what's the best way to word it? It's a little bit tricky. Okay, so when the boat is tilted, the area normal or perpendicular, the area normal / perpendicular to the wind will be reduced. And therefore, the mass of air hitting will be reduced. Hence, there will be a lower change of impulse, so therefore lower force. So hence, lower change. Smaller force, yeah. Okay, yeah, that should be fine. Okay, and this will be another 1 mark question there. Okay, so question D, due to the sideways component of the force on the wind, the velocity of the WH is in a slightly different direction to that of the hull. This slight difference in the directions creates an asymmetric flow of the water around the sides of the hull, which produces a sideways force on the hull of the WH as shown in the diagram on the right. Explain the sideways force produced by the water flow will have on the direction of the motion and on the ability of the WH to stay upright in the strong winds. Okay, so we know that the velocity of the WH will be not directly in the direction which it is pointing due to that component of force which is pulling it away from the direction that the boat is pointing in. So this sideways force helps to counteract that force by trying to pull the WH back in the direction that it is pointing. So in terms of forces, we have the sideways force from water flow pulls the closer to the direction it was pointing in. It does this by counteracting the sideways component produced by the winds. So counteracting the sideways component of the force produced by the wind. So that's in terms of the forces acting on the boat, but in terms of the torque as well. So we want to look at whether it's going to be rotating, and it's going to be if it's going to be rotating into the water, perhaps. So we'll be looking at the torques. So in terms of the torques, we know that there's going to be some sideways force produced by the water flow. So if we have the previous diagram, maybe I'll just try to draw the previous diagram again. So if we have this, I'm not a very good drawer, but okay. So this is going to be, again, it's going to be some sideways component of the force produced by the wind. So this would be force wind, or sideways force of the wind. Okay, so this would be like F sideways of the wind. And from the hull, there's going to be some force produced this in this direction. So something around somewhere. This will be the sideways force produced by water flow. So sideways from water flow. And if we're looking at the what the torques are producing here, so sideways from the water flow. So in this case, we have like the center of mass would be somewhere here. So this will be the center of mass of the WH. And if you look at both of these forces, even though they're pointing in different directions, they're on different sides of the center of mass. And hence, because they're pointing in different directions, they're actually producing torque in the same direction. So the F wind produces in clockwise torque. And F from the water flow, so F water, that also produces a clockwise torque. So a torque in the same direction as that from the wind. So therefore, there's going to be a greater angular acceleration in the direction that it is tilting in, and therefore it might be more likely for the boat to be it will be harder for the boat to stay upright in strong winds. So you can just say from diagram, both forces produce torque in the same direction. So both forces produce torque in the same direction. So therefore, greater angular acceleration. So great. Hence, less likely for the boat to stay upright in strong winds. Yeah, I think that covers the questions. So we're looking at both the forces acting on the WH as well as the torques acting. And in terms of the forces, it helps steer the boat back in the direction that was initially pointing in. And in terms of the torques, it actually acts in the same direction as out of the wind, so it might be more likely for the WH to actually tilt over. So I believe this is a 2-mark question, so you can get 2 marks. I believe 1 mark. What would make sense is 1 mark for the forces and 1 mark for the torques. Alright, and that's it for questions 1 and 2 for the scholarship physics. If you have any questions, I understand some of my explanations might not have been super clear. So if that's the case, don't feel free to leave a comment in the comment section below. I'll be happy to get back to you. And I hope to see you all in the second part where I go through question 3 and 4.